Well, good evening, everyone. I'm Charles Schultz, and this is the Randomizer. And today, our term pulled out of our digital hat is wavelength. Now, wavelength is an interesting term. It has different applications in different media and different types of signals. So, we're going to talk about, I'd say, three different varieties just to get a feel for the term. Before we go any further, I'd like to take everybody on a quick tour of schultzlaboratories.com or the virtualsciencecenter.com. If you'll go to the homepage for the virtualsciencecenter.com, you'll see a number of videos posted there, and one is a virtual walkthrough, a bit of a tutorial that shows you a little bit about what the facility is all about. Go ahead, watch that video if you haven't done it before, and get familiar with what it is we're doing. We're creating a whole virtual world for educational purposes. A lot of people talk about things like Facebook and Meta and how it's such an interesting place. Well, what we're devoted to isn't gossip and movies and cat videos, but actual educational efforts, so you can actually learn something. And if you've got kids and you want to teach them something about physics or astronomy or mathematics or music or genetics, we're adding new content all the time, and this is a great environment for them to learn in. It works best on a laptop or a desktop computer, and I hope that everybody has an opportunity to have a look at it and see what they think. Also, if you have an educational bent and you have to share your skills or what you've learned with people, contact us about setting up a digital virtual classroom or gallery for showing off your goods and what you've created and sharing your talents and learning with other people all over the world. So that being said, become a member, join, sign up, and help us grow and add more content. And I thank everybody who is supporting us at this time. We rely on you all, and we're very grateful for all of your help. Well, tonight on the Randomizer, we're going to look at the term wavelength. So what is it all about? It's easy to say that everything in nature happens because of waves, and it's simply information propagating through a medium in some way or another. A lot of us can go to the beach and watch the waves moving in the water. We get a pretty good idea of what it means. That's a good visual model and it gives you a feel for what happens with electromagnetic waves or sound waves. Because overall, the medium that you use doesn't really shape the wave so much as simply conduct it. When we look at waves moving on the surface of water, and let's start with a simple example, a small pond, and you drop a rock in the pond, and you realize that the ripples propagate outward from the center where that rock drops in. You notice that the waves all move at the same speed. You don't see waves moving faster than others and overtaking them, or if you do, it's a rare event. In water it can happen, but generally it doesn't. Water has certain properties. Its mass, its resistance to being moved or flowing, its viscosity is what it's called. And if you'll notice, syrup is very viscous and it has a much thicker, let's say waves propagate much less readily in it. In water, it's pretty thin. Its viscosity is fairly low, and the waves propagate at a couple of meters per second. So if you drop a rock in the water, you're going to see waves spreading out from that center point at a couple of meters per second, typically. And that will change based on the properties of the water itself. Now imagine the vacuum of space, and you think, well, how would a vacuum, which is nothingness, conduct a wave? Well, the fact is the vacuum isn't simply a nothingness. Nothingness generally refers to the presence or absence of matter and energy. And when you talk about the vacuum, it isn't just a blank zero or some non-responsive thing. It actually has properties which can be calculated and measured. To make it a little easier, let's start with sound waves. Now we know that down at sea level, with standard temperature and pressure, sound propagates at a known distance. And if you've ever stood away from a wall and you've clapped your hands and heard the echo come back to you, you have an example in hand that shows you that sound travels to that object, reflects off of it, and comes back to you. Now, interesting phenomenon like that can be measured, and scientists over many, many years did measurements and discovered quite a bit about the properties of air and water. And the waves that move through them, in water, of course, is just a disturbance on the surface for the most part, but the propagation of waves in air is usually called sound. And sound has a certain property. It's usually in a certain range of frequencies, like anything greater than 20 hertz and below 20 kilohertz is typically considered in the human range of hearing. You have to be almost 60 feet away from a wall, or a little less than 30 meters, about 27 meters, from a wall in order to clap your hands and hear an echo. That is the minimum distance because that's the time it takes for that sound to go out, echo, and come back and have a noticeable delay from the initial sound that you made. So an echo is simply a response when the waves strike an obstacle and come back to you. Waves can be shaped, moved, focused, reflected, or absorbed by different obstacles. And we see that all the time. If you've gone to the beach and there's a jetty or a line of rocks in the water that breaks the waves up, you will notice that waves coming in come through in a very peculiar manner, almost as if they're being emitted from a speaker. Well, the study of waves in this matter led people to understand about the wave nature of light. And Newton is well known for the experiments he did with prisms and the light coming through a small hole in the wall and splitting the light into all of its frequencies as it went through the shape of the prism. And his studies were very clever. He found that if he took a thermometer and he placed it in each of the colors and measured the temperature, he could get an estimate of how much energy was being carried to the thermometer by each color of light. Then he noticed something very odd. As he went below red, there was a zone directly below red that was not visible, but definitely heated the thermometer. And in this experiment, he realized that there were colors that we were not seeing, such as infrared, because they heated the thermometer even though you could not see a signal of light. Well, today, anyone with a digital camera, their phone, a security camera outside their house, you will notice that infrared lighting, or night vision lighting, as it's sometimes called incorrectly, infrared lighting picks up this light that's invisible to the human eye very, very easily and shows images in the dark. Some insects appear to pick up infrared as well. When I look at the security cameras outside the building here, I often see moths, for instance, or other bugs flying around the infrared lights coming off of the cameras. So it's a good indicator that they're seeing some of that light, even though we can't see it. If you do stand outside and your eyes are dark adapted and you look at an infrared source, you will often see a very dim red glow. And that's because the dye in your eye that picks up that color of light is not technically very sensitive to it, but it can pick up some of it. So what about wavelength? Well, we know when we disturb the water, there is a specific length or size to those waves. The same is true for sound waves, and the same is true for light waves or radio waves, electromagnetic waves. When we talk about wavelength, what we understand is a signal moves at a certain speed, and the speed of sound is roughly 1,125 feet per second, 1,125 feet per second. So in 1 second, when you clap your hands, if that signal traveled loud enough to be heard, in 1 second it would have gone over 1,100 feet. And a good rule of thumb, if you're outside and it's night and you hear the thunder, and you look around and you see a flash of lightning, and you go, "Oh, I wonder how far away that is." From the time you see the flash, count seconds. If it takes 5 seconds, the flash of lightning is roughly 5,000 feet away, 5,500 feet, or about a mile. So that's an easy way for you to measure the distance of the source of a flash of lightning. Now, light waves and sound waves are actually very different in how they operate, but they share a lot of similarities. If I took the wavelength of a sound wave and I divided it by the distance it traveled in 1,125 feet in that 1 second, I can tell you how long that wave of sound was. And for a 100 hertz tone, which is a very low oscillation, 100 hertz, then it would cover 11 1/4 feet in one wavelength. So a 100 hertz tone has a length from peak to crest down back to zero of over 11 feet. By the same token, by knowing the frequency of a sound and the speed of sound, how far it travels, you can determine how long the wave is. So the way you figure it out is wavelength, or lambda as it's often called, the length. Length is equal to the velocity divided by the frequency. So can we do the same thing with light? Absolutely, we can. If we take the wavelength of a signal and we multiply it, we multiply it by the frequency, we get the speed of light. And if we take the frequency of the signal and we divide the speed of light by the frequency, it will give us a wavelength. Now, what does this mean? Well, if we measure it out for sound waves, sound travels 1 inch in 74 microseconds, 74 millionths of a second. The speed of light, however, if you were to flash a light on or off rapidly, and somebody were standing far enough away that it took 1 second for that flash to reach them, they would be almost 300 million meters from you, or 300,000 kilometers. So if you turn it into English units, it's over 186,282 miles in 1 second. So a signal traveling at the speed of light, whether it's actual light, radio waves, X-rays, terahertz waves, microwaves, doesn't matter, television signals, all of them travel at exactly the same speed because they are the same type of energy, just at different wavelengths. People who are CB radio enthusiasts often say 27 megahertz. Well, that's the 11 meter band. Or if you're a ham radio frequency enthusiast, a ham enthusiast, that's the 30 megahertz band, which is the 10 meter band. Well, 10 meters times 30 million cycles is 300,000 kilometers, the speed of light. And so now you know, if you go up in frequency 1 order of magnitude, your length of your wave goes down 1 order of magnitude. So 30 megahertz, the ham radio frequency, is 10 meters. 300 megahertz, which is in the microwave ham band, would be 1 meter. If we continue in this method, if you get down to the wavelengths of, let's say, green light, around 500 nanometers, 500 billionths of a meter is about the size of a wavelength of green light. And if you measure that out, that means that 600 terahertz, 600 trillion waves of green light would fit in 1 second of the distance that a signal at the speed of light would move. Now, if I were to shine a brilliant laser at the moon and it were to hit a mirror and then come back to me, how long would it take for that signal at the speed of light to go to the moon and come back again? At the speed of light, the moon is 240,000 miles away, or 348,000 kilometers. At the speed of light, if we measure it out, the distance to the moon is a little less than 1.3 seconds. So if I flash my laser at the moon, in 1.3 seconds, it will have reached the mirror on the moon, and in another 1.3 seconds, it will have come back. Now, this is an interesting fact. During many of the lunar missions, reflectors were placed on the surface of the moon by the lunar landing vehicles. These retroreflectors, as they're called, contain something called corner cube or dihedral optics. They're special reflectors designed so that no matter what light signal strikes them, it exactly comes right back to the source. They're very much like the reflectors you see on bicycles. And in fact, the design of them is exactly the same. But they're made, in this case, out of silvered Pyrex glass. So these retroreflectors on the moon are used by shining intense lasers from observatories such as in Mauna Kea in Hawaii toward the moon in short bursts, and then they are measured as they come back with a telescope. And the timing can tell us the distance to the moon and how fast it's moving away or toward us to within fractions of an inch. So we can see that the moon would be receding at 3 inches per second, for instance. And we would know that that speed was good because we've gotten an actual optical signal to the moon on the reflectors that the Apollo astronauts left and back again to the observatory. Very simple method of measuring distance. So wavelength. In summary, imagine you have a wheel and the length of the wheel is the length of your wave, and you paint a dot on the rim of the wheel. Now, as the wheel turns, the dot goes around the wheel. One cycle is a complete turn of the wheel. Well, what if we put it on the ground and the dot was at the bottom and we rolled the wheel along? The dot would describe a sinusoidal wave or a sine wave. And one complete cycle from zero to its peak, down through zero to its bottom, the crest, the trough, and back to zero, one cycle. That's one wavelength, a complete all the way to the top, all the way to the bottom, and back to zero again. This is what we talk about when we mean wavelength. It is the distance of length of the signal, and however many of those signals happen in 1 second, that gives you the wavelength if you know how far the signal travels in 1 second. Speed of light, c, divided by the frequency, f, gives you the wavelength, lambda. And if you think about the wheel turning, every time it turns 360 degrees, you've gotten a complete sine wave out of it. That's the easiest way to understand what phase angle is, by the way. When we talk about the angle, the phase angle of a signal, we start with a zero reference, and we see how far that wheel would have turned for that signal to be that far out of phase. So when you hear about phase angle, that's exactly what we're talking about. How far a signal has advanced past some known reference, considering that it takes an entire revolution of the wheel for one cycle of that signal. So wavelength, that is the actual length of propagation of a wave, whether it's a sound wave, an electromagnetic wave, or a wave on the surface of a pool of water. So I hope this has been an interesting definition and some good examples for you. We've covered examples both in mechanical systems, such as waves in water, a liquid, the mechanical system of compression and rarefaction waves in air, known as sound, and the electromagnetic field carrying waves such as light, energy in the vacuum. So if anybody has any questions, the floor is open. And in the meantime, I'm going to encourage people to go to universesciencecenter.com or schultzlaboratories.com and become a member, sign up, take our classes every weekday at 6 p.m. Eastern Standard Time. Join us for the Randomizer Live. Bring your questions, your ideas, and this is an opportunity for you to go live on the air and let yourself be heard. Contact us if you want us to make a virtual classroom for you. We'll definitely get started on that right away. We enjoy adding content, and we love to work with the community. We want to see people learning and enjoying themselves. After all, if what you're doing is teaching you something and it's fun, you're going to keep doing it. That's just in the nature of things. Well, I don't see any questions. And so I'm going to read my quote for the day, and this is going into the weekend. I hope everybody has a great weekend, but here's our quote for the day. For I delivered to you, first of all, that which I also received, that Christ died for our sins according to the Scriptures, and that he was buried, and that he rose again the third day according to the Scriptures. This is 1 Corinthians 15, 3 and 4. And again, these are uplifting words. The fact that you can transcend death, what an amazing thought. I hope that everybody takes that with them, keeps it in their heart, and remembers that no matter how strange the world works, how evil things seem to be, how horrible and upside down it is, I read the end of the book and we win. Take heart in that. Well, everybody, I hope that you have a wonderful weekend. Join me again on the Randomizer Monday. Take care of yourself this weekend, and as usual, make the world a better place. I'm Charles Schultz with the Randomizer. Thank you.